we talk about frontiers, innovations, modern innovation in the aerospace sector, which focus on advanced propulsion systems, reusable launch vehicles, the AI and autonomous systems, CubeSats, this is the program I'm involved in, on-orbit servicing and manufacturing, space habitats, life support systems, communication technologies, space resource utilization, space tourism, and of course, other issues about energy. This I will present about energy in another session. So modern propulsion technologies already are moving beyond traditional chemical rockets. Electric propulsion systems like ion and Hall effect thrusters offer high efficiency for long distance travel. Another type, nuclear propulsion, both thermal and electric, could dramatically reduce travel time to Mars and beyond. Solar sails use photons from the sun to gently accelerate spacecraft over time. Reusable launch vehicles pioneered by SpaceX Falcon 9 and expanded with Starship of Elon Musk drastically reduce the cost of space access. And these rockets can actually land and be flown again, making spaceflight more frequent, sustainable, and economically viable. Blue Origin, in the same way, and Rocket Lab are also developing similar capabilities. Artificial intelligence is revolutionizing spacecraft operations. AI allows for real-time decision-making on planetary rovers, for example, NASA's Perseverance, and autonomous navigation for deep space probes. Ground control systems also benefit from AI, improving data analysis and mission planning. CubeSats, which are small, low-cost satellites that can be launched in swarms, they are used for Earth observation, communication, and even interdisciplinary interplanetary science. Advances in miniaturization allow these tiny spacecraft to carry sophisticated instruments, democratizing access to space. Spacecraft can now be refueled, they can be repaired or upgraded in orbit. Missions like NASA's OSM-1 aim to demonstrate this. So in orbit, 3D printing and manufacturing enables construction of large structures such as antennas or habitats that wouldn't fit in launch vehicles. What about space habitats and life support systems? For long-term missions, astronauts need sustainable habitats. So this includes closed-loop life support that recycles air and water, radiation shielding, and materials for modular and inflatable habitats. Concepts for moon bases and Mars colonies are being developed already by NASA and private companies. New systems, communication technologies like laser optical communications offer faster, more secure data transfer between spacecraft and Earth. Satellite constellations like Starlink create a global broadband network, improving this way communication even in remote areas and for future deep space missions. Space resource utilization. In situ resource utilization actually involves using local materials like lunar regolith or Martian ice in order to produce oxygen, fuel, and building materials. And this reduces the need to launch supplies from Earth, and it's crucial for sustainable off-Earth living and construction. For space tourism, companies like Blue Origin, Virgin Galactic, and SpaceX are making already space accessible to private citizens. Suborbital tourism is already happening, while commercial space stations and lunar trips are being planned, potentially opening a new era in civilian space access. And very fascinating, deep space exploration tools, because new technologies now enable missions far beyond Earth. These include radioisotope thermoelectric generators for power, autonomous navigation systems, highly durable spacecraft. So upcoming missions aim to explore Jupiter's moons, asteroids, and eventually send probes to interstellar space. Now, we mentioned about next-gen propulsion systems for deep space travel. The future of deep space exploration depends heavily on the advancement of propulsion technologies that are far more efficient and powerful than current chemical rockets. So here's an overview of some promising next-generation propulsion systems that are being developed or theorized for interplanetary and interstellar missions. Electric propulsion systems, the systems use electricity, typically from solar panels or nuclear power, to ionize and accelerate propellant. So ion thrusters, it's the Hell effect, and graded ion drivers, the working principles that use electric fields to accelerate ions. Of course, there are pros and cons. Pros that it's a high specific impulse, so talk about efficiency. The other type, it's what we call variable specific impulse magnetoplasma rocket, which uses radio waves to ionize gas and magnetic fields to direct the plasma. It's good for fast transit times. So there are pros and cons for each of these types. Nuclear thermal propulsion. Here, a nuclear reactor hits a propellant like hydrogen, which is expelled through a nozzle. There are all, at the same time, of course, political technical challenges here, but we talk about twice the efficiency of chemical rockets. And nuclear electric propulsion, a nuclear reactor generates electricity to power ion here or Hall effect thrusters. It's very high efficient, and it's about long duration thruster. Fusion propulsion that uses nuclear fusion to generate thrust via plasma exhaust or electricity. So we talk about extremely high energy density. And antimatter propulsion, here matter and antimatter annihilation releases massive energy used for propulsion. So, of course, here's the pros and cons. Because we're talking about the highest theoretical energy density. The solar cells and photonic propulsion use radiation pressure from sunlight or lasers to push large reflective cells, so there's no propellant needed. This can achieve very high speeds over time. And beamed propulsion, the ground or orbit-based laser microwaves, which requires, however, precise beam aiming and vast infrastructure. And the theoretical and exotic concepts, it's a speculative idea, Alcubierre warp drive. This is an idea involving space-time distortion. The EM drive, which is actually controversial nowadays, and quantum vacuum thrusters, which is under investigation. And here if we see about the maturity level, some of these types are already on an operational level, some others are in experimental level, others in development, others are on conceptual, experimental, fusions on experimental level, etc. And the use case for each one is visible here in this table. And about thrust and efficiency, others are low and others high, medium. Now, what is the future of space-based solar power? I think it's very interesting. When we talk about space-based solar power, this refers to collecting solar energy in space, where the sun shines almost continuously and transmitting it to Earth via microwave or laser beams. Unlike terrestrial solar panels, these systems aren't affected by weather, day-night cycles, or atmospheric interference. So what is the current status here? Agencies like NASA, the European Space Agency, the China's agency, and Japan's are investing already in these concepts. In 2023, Caltech launched the Space Solar Power Demonstrator, and they try to test key technologies like wireless power transmission. And in the private sector, we have seen companies and startups which are exploring already commercial pathways. So the key technologies about this is ultra lightweight solar arrays in order to minimize launch costs, wireless power transmission using microwave or laser to beam energy to Earth-based receivers, so RIC-TINAs, and autonomous assembly in space where robots or modular satellites assemble large arrays, high efficiency photovoltaics, which maximize energy yield in orbit. So the major challenges at the same time that it's about the infrastructure, the launch infrastructure costs are still high. Current transmission efficiency is relatively low. The safety, all these concerns about microwave, laser beams, sometimes they hit unintended targets, and there are no clear global framework for this concept. So we'll talk about serious challenges. For a timeline milestone here, what are the expectations? 2025 until 2030, we will have more tech demos and possibly pilot scale systems, more commercial pilot projects until 2040 intergovernmental consortia. And from 2040 and 2050, we will have full-scale farms feeding power to grids, etc. What are the key drivers for success? The falling launch cost, it's possible, advances in space robotics and AI, international cooperation, definitely, the climate change urgency, which pushes clean energy innovation. And why this matters? Because if this is successful, solar space-based power can deliver base load renewable energy 24 hours a day, reduce reliance on fossil fuels, it can power remote or disaster hit regions, and it can enable clean energy. Now, about AI and robotics. AI and robotics space exploration are transforming how humanity explores, understands, and operates in space. And as missions become more complex and venture farther from Earth, artificial intelligence and robotic systems are essential for autonomy, efficiency, and safety. So what is the role of AI and robotics in space? If we talk about autonomous navigations, then rovers and probes use AI to navigate rough terrain, for example, NASA's Perseverance. If we talk about data analysis, AI accelerates image recognition, geology mapping, signal interpretation, concerning mission planning, algorithms, optimize spacecraft trajectories. There are robotic arms and assistants which handle in-orbit repairs and inspections. So it helps if in the field of maintenance and repair, and definitely it's about human-AI collaboration because AI supports astronauts in habitats, operations, and in general decision-making. Some key examples, for example, NASA Mars rover, Curiosity Perseverance, here AI helps identify rock samples and choose navigation paths. Perseverance auto navigation system enables faster autonomous movement. The European Space Agency Rosalind Franklin rover uses onboard AI to make real-time decisions about soil analysis. Robonaut and Simon, here we have robot assistants aboard the National Space Station to help astronauts with tasks and even provide social interaction. The DART mission, which actually used autonomous navigation to crash into an asteroid, testing planetary defense capabilities, and lunar Martian construction. Here we have robotic 3D printing and autonomous machines which could build habitats before astronauts arrive. And the AI technologies are used, of course, computer vision for identifying terrain features, obstacles and objects, machine learning for predictive maintenance, pattern recognition and adaptive behavior, natural language processing for enable voice command interfaces for astronauts, and swarm intelligence, which is about coordinated control of multiple small satellites or robots. On the other hand, of course, there are challenges because if you think about latency, it's long communication delays require high autonomy. Reliability, because systems must work in extreme conditions with little room for error. It's about ethics and safety, ensuring trust in AI decisions, especially in crewed missions, and power constraints because limited energy availability requires efficiency. What are the future prospects? The time frame forecast that until 2030, there will be increased use of semi-autonomous rovers, AI co-pilots on space stations. Until 2040, we have full robotic constructions of habitats on Moon or Mars. And until 2050, human AI colonies with robotic agriculture, repair, and scientific research centers are expected. Why all these things matter? Why robotics matter in space? Because this can enable missions to unreachable or hazardous environments, very important. So it reduces the danger and all these hazardous conditions. Reduce costs by minimizing crew needs. It accelerates definitely scientific discovery. We talk about real-time data processing, and it paves the way for sustained lunar and Martian presence. Another field very popular is what we call low Earth orbit satellites. This operates actually at altitudes between 160 to 2,000 kilometers above Earth's surface, and their proximity to Earth offers several advantages, making them increasingly vital for modern applications. So these low Earth orbit satellites support fast, low latency communication, which is ideal for internet connectivity, for example, Starlink or OneWeb, for mobile and remote communication services, for real-time data transmission. And because these satellites are closer to Earth, signals take less time to travel, enabling near instantaneous communication, which is a key advantage over high orbit satellites like those in geostationary orbit. If we think about surveillance and Earth observation, these satellites are ideal for high-resolution imaging, making it essential for military and border surveillance, for environmental monitoring, deforestation, climate change, pollution, for disaster response, floods, wildfires, hurricanes, for agricultural mapping and urban planning. Their lower altitude allows these satellites to capture finer details and revisit the same location frequently, making them highly effective for real-time monitoring. For data collection, because the satellites collect a wide range of data used in weather forecasting, climate research, and atmosphere analysis for tracking wildlife, sea levels rise, and ice coverage, and scientific experiments aboard platforms like the International Space Station. So these satellites play a crucial role, of course, in building global data sets for research, for industry, and policy making. And last in the last part, it's very, very interesting, very trendy. Already in schools, Greek schools, we try to integrate what we call biomimicry. So bio-inspired technologies for space survival. What is this? Bio-inspired technologies or biomimetic technologies draw design and functional inspiration from nature in order to solve complex engineering challenges. So in space, where extreme environments test the limits of human survival and machine durability, nature offers surprisingly effective models for innovation. So we talk about self-first healing materials, which are inspired by human skin and plant tissues. Here, researchers are developing materials that can repair microcracks or punctures in spacecraft and spacesuits. This could reduce the risk from micrometeoroid impacts and extend equipment life without human intervention. Another example is water recycle based on desert creatures. Animals like camels or beetles have evolved to survive with minimal water. So these organisms inspire efficient water recovery systems, helping astronauts recycle moisture from breath, sweat, and waste to create closed-loop life support systems on long missions. Or photosynthesis-inspired life support. Plant processes are being mimicked to design systems that actually can convert carbon dioxide into oxygen, and they can use algae and bioengineered organisms for air and food regeneration. This can reduce dependency on Earth resupplies during long missions. And gecko-inspired adhesion. Geckos can stick, these are small, mostly carnivorous lizards, which can stick to surfaces without glue. So engineers are actually creating adhesive pads for astronauts' robotic arms using similar microstructures, enabling movement and attachment in zero-gravity environments or on spacecraft exteriors. And swarm robotics inspired by insects like ants or bees cooperate in swarms to build and explore. So their behavior informs modular self-organizing robots that can explore planetary surfaces. They can assemble structures autonomously, and they can adapt it to new environments with minimal commands. Finally, tardigrades are microscopic organisms that survive extreme radiation vacuum conditions. Scientists are studying their DNA protection mechanisms to design radiation shielding suits or enhance human cell resilience for deep space travel. Already, I said before, here in Greece, there are many schools, and in Europe in general, that try to integrate biomimicry in the classroom through different kinds of school projects and activities. It's amazing. And finally, about the space tourism, the commercialization of space is entering a new era, shifting from purely government-led missions to private ventures, offering space experience to civilians. So with advancement in reusable rockets and orbital infrastructure, space tourism is becoming a viable industry. Yes, we have the case of Blue Origin. Suborbital flights allow passengers to briefly exit Earth's atmosphere to experience weightlessness and view the curvature of Earth, all within a single short mission. So Blue Origin here offers a fully autonomous rocket-based system. The focus on how the passengers can spend 10 or 11 minutes in space. I have collaborated with Blue Origin actually in Greece, the Hellenic Physics Society, the Greek Physicist Society is collaborating with the Blue Origin with some about some space programs in schools. So already having experience with Blue Origin, and Virgin Galactic. Virgin Galactic is another company which uses space plane launched from a mothership, and it emphasizes luxury experience, smooth ascent and descent. So of course, the commercial space stations, their private companies are already building the next generation of orbital platforms. Action Space and others plan to offer private research labs, long-term stays for private astronauts, tourists, etc. Lunar tourism and missions. The moon is the next major frontier for space tourism. Space Starship is set to carry private citizens around the moon. And NASA's Artemis programs, while government-led, opens doors for private partnerships. So future plans include lunar landings for tourists, moon hotels or habitats, rover excursions. And here is a program where I'm involved. It's called the Mission Shaktisat. It's an amazing program which tries to unite 12 million girls from 108 countries. So what we're doing here in Greece, I have some Greek students which will attend a MOOC. And after this MOOC, they will get technical training. We will visit India. We will try to build satellites, mini satellites, which will be sent to the moon through the next Chandrayaan-4 mission. We all know the Chandrayaan-3, which was very successful, the historical space mission in India. It was organized by Space Kids India. And of course, our objective here is how to empower girls, especially girls from rural areas, in this historical milestone. And at the same time, we talk about how girls can be involved equally in STEM education, so equal access to this, how to ignite passion to them, how to break down all the gender stereotypes when it comes to STEM education, how to break barriers. Here, before concluding, here is, it's not worth it to mention that behind the Chandrayaan-3 mission to the moon, there were women leaders, and this fact was uploaded worldwide. And with the Greek Astronomy Space Company here, we're organizing many events, especially about women. Thank you very much for your attention.